We're now going to make the connection between Newton's second law and the idea of a quantity of motion that we call momentum. So once we get done today, we should be able to define momentum, calculate momentum, use the momentum of an object to create a position time graph for that object, and create a velocity versus mass graph to represent the momentum of that object. We have talked about the impulse being the force applied during the time of an interaction. Newton's second law says that if we apply enough force to an object, then the object's motion will change. While we typically refer to Newton's second law in its mathematical form, this isn't really how Newton originally thought about it. Newton took a few ideas from Aristotle and described objects as having some quantity of motion. This quantity depends on two things. Say we have a tennis ball that is moving along. Its motion can be described as having some quantity, whatever that is. What if it was moving faster? It follows that we could describe it as having more motion, right? So our quantity of motion would go up. So the same object moving with a faster speed would mean that it has a larger quantity of motion. This lets us say that Newton's quantity of motion depends on an object's velocity. What if we have our same tennis ball moving at the same velocity as a bowling ball? That bowling ball is going to have a lot more mass than the tennis ball. Do you think it would be fair then to say that it would have a larger quantity of motion than the tennis ball? That makes sense. Which one would be harder to stop? Think back to the idea of Newton's inertia, right? Object in motion will stay in motion. If it has more motion, it's going to have more inertia. So that gives us another variable to consider when we talk about Newton's quantity of motion. So velocity and mass both describe an object's quantity of motion. And the term that we give this is momentum. We can think about momentum in terms of an object's mass and velocity, and use those properties to describe its motion. Take a large boulder and a small stone rolling down at the same speed. Which one would have more momentum? The larger boulder, since it has more mass. What if you compare two boulders with the same mass and one is moving faster? The faster boulder would have more momentum since it has a faster velocity. What about a boulder at rest? How would we describe its quantity of motion? Well, it has no motion, so it would in turn have no momentum. So something that is not moving will have zero momentum. Here's something to think about. Can a bowling ball and a car have the same momentum? A car is a lot bigger than a bowling ball. What would the ball need to be doing to make up for that difference in mass? It would need to be going pretty fast. So here's the relationship we have with momentum. If we increase the velocity of an object, its momentum will increase. Vice versa, if we slow it down, its momentum will decrease. The same things happen with mass. An object with a larger mass will have a larger momentum. So both velocity and mass have a direct relationship with momentum. If one of them increases, so will the momentum. If one of them decreases, then the momentum will decrease. This lets us calculate momentum by taking the mass times the velocity. P in this equation is the momentum. The closest anyone can find as to why is P and not M is because Newton was referring to this property in terms of an object's impulse. I is a terrible variable to use since it looks a lot like 1, so P it is. M is the mass as it is measured in kilograms, and V is the velocity in meters per second. Multiplying mass and velocity gives us the terribly awkward label of kilograms times meters per second for momentum. Unfortunately, no one has come up with a way to shorten this unit into something more manageable, so kilograms times meters per second it is. Now, momentum is a vector quantity, so we need to include direction whenever we are discussing momentum. For our purposes, we're going to stick with the convention that an object moving to the right or to the east or up will have a positive momentum. An object moving to the left or to the west or down will have a negative momentum. So let's look at an example and see all the different ways that we can represent this. Say we have a 6-kilogram pumpkin traveling to the west with a velocity of 5 meters per second. What is its momentum? Well, first off, let's start with the knowns in this problem. We are given mass of 6 kilograms and a velocity of 5 meters per second to the west. This would mean we have a negative velocity, so we want to make sure we include negative in that. We're trying to find momentum, and the formula we have for momentum is mass times velocity. This seems pretty straightforward in that we can take the mass times the velocity and get a momentum of negative 30 kilogram meters per second. All right, so now we're going to take this problem and represent it in a couple other ways besides just numbers. The first thing that we can do is create a position time graph for this motion. Remember, a position time graph tells us where an object is in space at any given time. Also remember that the slope of a position time graph tells us the velocity of the object. What do we know about the pumpkin? We are given a velocity of a negative 5 meters per second. We don't know where it starts, but it doesn't really matter. We can choose our own position. Let's say that our pumpkin starts at the top of the graph, which is 30 meters because, again, we get to pick what the scale of our graph is. If the pumpkin is a velocity of negative 5 meters per second, where will it be after 1 second? It will be at the 25 meter mark. After another second, it will move 5 meters closer to the reference point, and then another 5 meters every second after that. Using this information, we can draw a position time graph for our pumpkin that is moving with a velocity of negative 5 meters per second. Now, this next representation is a new one. We've just talked about how the momentum of an object depends on its mass and its velocity. So if we build a graph that has mass on the x-axis and velocity on the y-axis, we can show the amount of momentum it has in graph form. We know that the mass of our pumpkin is 6 kilograms. This is essentially a bar graph, so to plot this on our graph, we are going to measure out 6 spaces. It does not matter where on the graph you have this. You can start on the very left, on the very right, or in the middle, as long as you have 6 open spaces. On the y-axis, we are going to put our velocity. We have a velocity of negative 5 meters per second, so we are going to go down from the 0 line 5 spaces. From here, we're going to make a rectangle that represents our bar that is represented by the mass on the length and a velocity on the width. What does the area of this rectangle represent? Well, we already know that the formula for momentum is mass times velocity. So that must mean that the area of our rectangle, which has mass on one side and velocity on the other, represents the momentum of our pumpkin. So that was a lot of information in a very short amount of time. So are you able to define momentum? Can you calculate momentum? And can you use momentum to create a position time graph for a moving object and create a velocity versus mass graph to represent the momentum of an object?